Welcome to the Marcellus Shale Lecture Series. I'm Marcus Bursick, the chairman of the Geology Department here at UB, and this is the fifth one in the series. And so it's really nice to see everybody here. We had a really high sign-up for this talk, I noticed. I think it's because of the title, probably. So the format's going to be the same as it's been before. At the end of Rich's talk, though, I finally have been able to put the presentations up on the web, and I'll flash the website when we start the question and answer period, so people can look at the talks that are up so far. I think only have a link to the talk by the speaker last week, Greg Silvas. But I do have the PowerPoints up from the previous talks. So I'll flash that after Rich talks here. As before, the format's the same. I hope people did register as usual, and it's good for us to know who's out there, and plus we can send you emails letting you know about any changes that happen. We'll start with I'll say a few introductory remarks. Rich will give his talk, and then we'll do the brief timeout, a couple, 3 minutes, to allow people to stretch and take off if they need to. Then we'll start with the question and answer period, and we'll start with students again as usual. And we do have some students from JCC this evening with us, but I just talked to them, the instructor, and they'll have to take off right after the talk. So a lot of students from UB can't be here today because this is the start of it's almost about to start finals week next week, so they're feeling the pain right now. So I'm not sure how many made it, but we'll leave a little bit of time for students in case we got a few questions. And then we'll move on to the general public's questions. The speaker this evening is Rich Nyahay. He got his BA in geology from SUNY College at Plattsburgh. He was employed as a geologist with the New York State Geological Survey and the State Museum from 1988 to 2008, and he ended up there as the geology and geophysics manager of those programs at the State Museum. He joined GasStem as a geology and geophysics manager in 2008, and he's here to talk to us today about drilling and hydraulic fracturing. Rich Nyahay.
Welcome. Thank you for coming out this evening. It's great to see you all. When I left the survey in 2008, gas was at $14 MCF, and oil was $140 per barrel. And I'm saying to myself, this is a good time to leave the survey. I have 20 years. I'm ready to go. So basically, I joined up with a company called GasStem. They're out of Montreal, Canada. And they were opening up an Appalachian branch here in eastern part of New York in Otsego County. And they said, would you like to head up? I said, sure. They said, well, we're going to probably drill 5 vertical wells, and we're going to maybe do 1 or 2 horizontals. And I was salivating. But little did I know that the timing wasn't right for any of it. Everything has all come crashing down to a certain extent. But the good part is that we're starting to listen, and you are the force behind that. We are listening to your comments, and it's just a testament to your will. What we're going to talk about tonight is the Ross number 1. And the Ross number 1 was fracked, but it was fracked using the old SGIS rules, not the new rules, but the old rules. And basically, that was you can be allowed to use 80,000 gallons of water to frack. Now, what kind of makes the Ross unique is that we fracked both the Utica and the Marcellus. So what I want to do is kind of tell you that story tonight, show you pictures that maybe you've never seen before, talk about things that you've never heard before. So let's kind of get started. This is the only geology part right here, and basically, we're looking at the Marcellus Shale. That's everyone's interest. But my interest, and a lot of other people's interest now, is the Utica. The Utica is starting to take hold in southwestern Pennsylvania and southeastern Ohio. They call it the Point Pleasant in Ohio. Again, it's the Utica in Pennsylvania. And everyone also knows about the Marcellus Shale. That has had enough headlines for many decades. So before there was environmental awareness, there were two wells that the company that we partnered up with was called Covalent Energy. And they drilled two wells in northern Otsego County, the Pulse number 1 and the Shekels number 1. Again, they were drilled under the old SGIS guidelines, and they used approximately 39,000 gallons of water. Things have changed since 2007. So we'll take a real closer look at that tonight. But think about this. Here were two wells. Where did they get rid of that water? I've asked. I can't tell you. All right. Basically, how many of us have gone to these type of meetings? I've gone to probably at least 100. And the reason that I like this picture is because we have our president. Our president is Orville Cole. So those who know Orville, if you can find him, that's the audience participation part of this program. Again, this was taken out of the Binghamton Press and Sun. And those of you who don't know who Orville is, he's the one with the happy face right there. This is what I read right before I started my job. And I'd like to read it to you tonight because basically I think it has a lot of questions that a lot of people will be talking about this evening. And this was written by a candidate for state senate. His name was Don Barber, supervisor in the town of Caroline. And this is what I keep on my wall every day because these are the questions that I want to answer. This is the ownership. What will our communities be like with a gas well every mile? What does a drilling program entail? Where will 1 million gallons of water required for each well come from, and will the withdrawal process be monitored? What chemicals are the drillers mixing into the water? What happens to the water mixture after drawing it from the well? No treatment facilities have yet to be identified. Since there's no guarantees that aquifers won't be affected, what recourse is available for property owners? Will local taxpayers have to pay for roads damaged by drilling process? Will gas lines be buried on our properties? Will leases hurt our ability to sell our properties? Well, back in 2008, I didn't have a lot of answers for those questions. But tonight, I do have some answers for those questions. And I encourage you, if you have more questions, please ask them. Well, I thought of this part of the world. I assume that you've seen this slide, but if you haven't, this is Chautauqua County, and these are all the wells in Chautauqua County. This is Otsego County. This is where we're drilling. There's maybe 13 wells here. There's over 10,000 here, and the majority of them have been fracked. And the formation that they fracked is called the Medina Sandstone. Somebody has said it before, it's like drilling through concrete. And that kind of describes what happens in shale, too. It's very tight. These are very tight. They don't have too much porosity, not too much permeability, so that's why they have to be fracked. So again, I've always looked to Chautauqua County when people say to me in Otsego County, what is our county going to look like? Well, it's not going to change too much, except you'll have a lot more dots when they make a map. Other than that, the hills will be the same, the water will be the same. So one of the questions the first question that you saw, what will our county look like when we have a well every mile? You will not have this, because when they start drilling for shale, again, basically they'll be making square mile blocks, and it won't be for every mile either. People are starting to take a look at this. Gas is now at $4.40 per MCF. It's not at $14 per MCF, so basically their exploration dollars have to take them a long way. So they just can't be poking holes in the ground like they did over here. They'll have to be very judicious with their funds. So let's walk you through what happened when I got the Ross permit. The Ross permit took over a year to obtain. And I'm not joking. Basically, the Covalent applied in May of 2008, and we've got a permit June 1st, 2009. Again, What do you have to do? You have to declare a target formation. And in the first well that we did with the Ross 1, it was the Utica. Okay, we also met with many divisions in the New York DEC. The Mineral Resource Division basically regulates the division, but we spent many hours with their Water Resources Division, and you'll see why. One of the things that you have to do is you have to declare what type of well casing that you're going to use in an application. Again, this well casing is probably the major thing that everything has to evolve around. If you're going to have a leak, it's going to be that the casing wasn't connected correctly or you had a poor cement job. Frac constituents to be used are submitted for review to the DEC. The frac that you use is submitted. It is reviewed. The public may not know about what chemicals will be going in, but the New York DEC reviews those chemicals, and you are given permission to either do it or not do it. If your chemicals don't meet their standards, you're denied. If they do, then you're allowed to frac. And it's basically you can't change the frac constituents before or after. It remains the same. You also need a plan for containment and disposal of frac fluids. This is also submitted submitted for review by the DEC. If you do not have a plan for containment or disposal, you do not get a permit. End the sentence. And also, for disposal, you not only have to have one plan, you have to have a backup plan behind. And basically that means what we did was we delivered our frac fluid up to Watertown. So we had to have correspondence between the New York DEC, Watertown, saying that they would take the frac fluid, and the list of rules that began from that point on were amazing. This is a word that no one throws around a lot, but it's an important title. It's called Headworks Analysis. We've heard just this past week that Pennsylvania waste treatment plants will not be taking any frac waters. Probably one of the reasons that they won't take it is because that their Headworks analysis was not either up to par, up to snuff, or that their waste treatment plants could not handle it. Who knows? But the problem is in New York, if we're going to proceed, there are 4 approved industrial pretreatment programs in the state, and one of them was Watertown. And the big word that we heard about was Headworks Analysis. And this Headworks Analysis is part of their permit program. And without a revised Headworks Analysis, again, you'd probably be denied taking any frac fluid to a certain place. So what was the most important thing that we did? The most important thing that we did was develop baseline studies. And what you see here are a bunch of wells, okay? Now these are wells in the DEC database. And basically right now, if you drill a water well in the state, you have to register that well with the DEC. And it basically just tells you the depth and the name and another characteristic, maybe 3 characteristics. So with all these wells right here, all I had was some depth information. I didn't have any geochemistry, nothing. So what we were luckily to have, there's a lot of studies that are local, county, and state agencies. And in this area where the Ross is, there's SUNY Oneonta and Hartwick College, and they both have master's programs that deal with water management. So their libraries were great to go through because basically we could start to piece together more information. What we also did is we sponsored an undergraduate. We sent this undergraduate to collect as many water samples as she could get around the Ross 1. Again, her deal was that she got to do an independent study and then do a poster for 2 seasons at GSA. I don't know if any of you were at the recent GSA. Tiffany McGivern was her name, and you've probably seen our data. So these were the analytes that we tested for. Here's some of the major elements over here: calcium, magnesium, sodium. But here's the 2 major ones: strontium and barium. What we found some elevated lead levels in certain places. We tested for organics, gross alpha beta, methane when we could detect it, and that's pretty important because apparently, you know, a lot of people are claiming that there's methane in their water wells after drilling occurs. So doing a baseline test, you can kind of determine the methane, and we'll talk about it a little bit more further down the line. Alkalinity, TSS, TDS, total dissolved solids, chlorines, and sulfate. Now here, pay attention to this little disclaimer here. Our basic water tests start at $700. Now I've heard claims that some people say, well, if we tested our water, it would cost us $30,000. But they would be testing for a lot of stuff. But again, we've developed a bunch of analytes that we test for. And again, our tests start at $700. And in certain wells, once we think we kind of notice something, we could work up or down from that number. So here's the Ross well right here. And as you can see, these blue dots are all the places that we tested for. 18 residential and 12 surface waters. The red line represents a mile radius. Green line represents 2-mile radius. The current regulations right now are focusing anywhere from 1,000 to 2,000 to 2,500 feet. It'll be interesting to see what the DEC comes out with. In the beginning, you just had to get one permit, and this was from the DEC. And again, this has to be posted at the front gate. But remember when we looked at those questions, they said, who's going to regulate water withdrawal? Well, we are in the Susquehanna River Basin Commission, and those responsibilities have now been usurped by the Susquehanna River Basin Commission, which is pretty good. So now, what you also have to do is you apply for a permit from the DEC, but you also have to apply for a consumptive water use permit from the Susquehanna River Basin Commission. And as you can see here in this permit, we're allowed to use 80,000 gallons per day. So again, that's what we were looking at for, and that's what we got. Also, you have to have an approved water source. If you are going to withdraw all this water from somebody's well, it has to be approved, since we're in Otsego County, by the Susquehanna River Basin Commission. That process can take up to a year. And this becomes pretty important because the more water sources you have, or more approved water sources you have, on occasion, things happen. A road is washed over, and then you can't get to your water source. So it becomes important to have a backup source. So again, most companies, if they're pretty diligent about what they're doing, they're going to have a few approved water sources. Now, you can have an approved water source from taking river or water out from the river. But again, it's a plan that you submit to the Susquehanna River Basin Commission. And again, it takes maybe 3 to 4 months, sometimes a year, to get that approved. It's not overnight. They're pretty busy. They don't like to be pushed, and they will not move very far from their positions. So, on our odyssey to get a permit for the Ross, we needed a frac sample. We did not have a frac sample. So what we had to do, we talked about the 2 wells from northern Otsego County. We had to go in the middle of March, you can kind of see the snow here, and basically go back into the Shekels well here and try to get a liter of frac water from that hole. So we were bailing. We had a bailing unit here. And the best we could do after 4 hours was maybe 3/4 of a liter. So again, what we had to do is apply for a flare permit, and that's no easy task. Go back to the DEC saying that we have to flare the well so that we could kind of get the water to come back up out of the hole. And even when we were flaring the well, it was dry. So what we got was 3/4 of a liter. And the reason that we had to do this is because we're going through the process now of talking with the Water Resources Division, and they wanted a sample. They wanted to test for things. So back in 2008, we analyzed for gross gamma, metals, and volatiles. And these were the tests that they wanted run for 2009. Again, additional tests. Before we were even to start talking about a permit, they wanted tests and they wanted data. Again, what we did was run some radiometrics on this Shekels #1, and I'll bring your attention down here. Uranium-235, 6 picocuries per liter. Now again, let me bring you over to this side. Discharge limits to sewers as part of New York state law is 3,000 picocuries per liter. So again, we were well under limits here. So finally the big day comes and we get the Ross drilling permit. Here's the title page right here, and there's the 8 other pages that followed it of instructions. Usually a drilling permit to drill was maybe 1 or 2 pages long. As you can see, there's many stipulations here to follow. And again, you do not follow those stipulations, you could be fined or you could be shut down. That's the end of the story. They don't care either way. Okay, let's start to take a look about what we did. Oops, sorry. We started putting silt fencing around, and then again, this was that northern face that was facing the water body right back here. So again, silt fence and bales of hay around the perimeter of the site. And the site is up here, just up the hill. We used nothing but closed systems. No ponds, no open pits, no line pits, steel tanks to hold the water, and steel tanks to hold the well cuttings. Because at the time, well cuttings were considered hazardous. Here, this demonstrates the power of the DEC. When we had our permit and we received it back in June, what we didn't know about is this, stormwater pollution prevention plan. And basically what these do, here's the upper part of the section, here's the access road, and there's a drainage ditch right along, and here's the lower pond over here. And these are stormwater prevention ponds. These are not ponds that are used for frac fluids or anything else or cuttings. What happens here during the heavy rains, silt is directed toward these ponds right here, and it's basically allowed to sit, and if the water gets high, the sediment settles to the bottom. Again, protecting the environment more than anything else. And what's interesting here, it didn't become law until May 31, 2010. Again, we were doing this in 2009. Now, can the DEC change the rules and regulations on you at the stop of a dime? They can. And will they do it? Yes, they will do it. Now let's take a quick look at what they look like. Basically, everything is graded down to here. You see how the water comes through in here, basically comes down to here, and there's an outlet over here. And what happens is basically the outlet is higher than these banks here, and the sediment is allowed to settle, and the clear water, again, is then directed to the water body. And the same thing happens at the bottom. The drainage ditches along the side of the road come down through here, settle down here. You can see the outlet there. It's a lot higher than where the base of the catchment pond is. Also on hand, when you build these types of pollution prevention pits, you need it to be inspected by an engineer who designed it. They come out every week to check that the grass is grown correctly, that the water basically flows out without any settlement getting any place else that it doesn't need to happen. Just another expense, but if you want to drill, this is part of the game. Here is the most important part of the whole program. It's casing. Everything happens because the casing job is not done correctly, the cementing job is not done correctly. Range Resources is going to a 5-string casing. You can count them. 1, 2, 3, 4, 5. Now, the conductor casing doesn't extend down all the way, but this is the beginning of the hole. But it's back from a steel casing and cement behind it. Same thing happens for this intermediate type casing. Steel casing, cement behind it. Now, fresh waters are generally less than 500 feet deep. When we were doing our baseline studies, we found one that was about 620 feet deep, roughly about 1.5 miles away from the Ross number 1. So what that says in New York state law is that we have to put casing down at least 75 feet past 620 feet to protect that aquifer. Again, without doing baseline studies, maybe that would have been missed. But again, the general rule is 500 feet. And then with every casing string, it's cemented. And just think, more than 1 million pounds of steel casing in each hole. So let's go through the Ross 1 casing program. Conductor was set through glacial till to sit on a solid bedrock base. We started with a 16-inch to 126 feet, and then a 10-inch to 138 feet. That doesn't make any sense. Well, what happened is that this 16-inch conductor pipe hit a big glacial boulder that it couldn't get through. Again, this is a massive boulder, so what they had to do is re-drill the hole down using a 10-inch drill to 138. Then again, 7-inch surface casing was set to 780. Why? Because we wanted to be below that 620 feet. Again, 4.5-inch casing is set to 4950, which was the total depth of the Utica well at the time. And again, this is cemented all the way to surface. Cemented to surface. Cemented to surface. There are no lags in between. So now I'm just going to show you some pictures of what it kind of looks like. Over here you can see the 16-inch conductor. It's going down through the hole. It's just being pushed down through the glacial till. And glacial till is nothing but a lot of clay and boulders. And who's on site? The DEC inspector. There's his license plate. He was there more times than not. I can't say he was there every day. It seemed like he was there every day. And when he wasn't there, we were in telephone contact. Morning, noon, and in the afternoon. 7-inch drill casing here. You can kind of see the strings being lined up. Here's a close-up of the 4.5-inch production casing. These are many pipes. There's a coupler that's screwed on. Again, cement truck. The cement, you've now set your casing and now you have to cement it. Now, I don't know if you guys recognize this as a cement truck. Most people wouldn't. Again, but this is the cement truck that the oil and gas industry uses. Basically, the cement is mixed here and it's piped down and it goes to the well. We'll take a closer look. And what do they pipe it through are these small, skinny tubes that they have to put in between the casing strings. And you can kind of see them kind of setting it here. They're carefully doing that. Again, here's water that is used to mix the cement. Again, it gets pumped through there. And then you can kind of see the skinny tubes that are right along inside the different casings. And what's happening here, the cement is pumped down and basically comes back up through and is being the excess. That's how we know we've done a pretty good cement job once we start to see returns coming up. And again, a vacuum truck is right behind. And here they have this guy with it looks like he's just doing water, but it's a cement slurry. DEC inspector sitting there watching it. And probably the question that you have, and this is the one thing that I learned while I was a new employee, was what happens to this cement over here in this vacuum tank? It's going to harden up. They use a little ingredient called sugar. And basically, once they put the sugar and they mix it with the cement, it won't harden. So I thought that was kind of interesting. This is what it looks like when it's all done. You can kind of see the cement donut around the hole. See it there, looking down, across. Again, notice there's a lot of gravel around the hole. So we're done with the surface casing. The site is cleared, and we get ready to bring on a bigger rig to finish the drilling to TD. So notice that there was a lot of activity around this well. Again, cleared out, You know, drill string is sitting right there ready to go, compressor going there, water tank, some more drill strings. Here they put on what's called the BOP, or the blowout preventer. And what does this do? It prevents the well from blowing out. And there are 3 rams in here, basically little annuluses that circle and close up in case of an emergency. Again, there's pipe that come out from that. Again, here was the first one didn't fit so well, so we had another one coming back. So again, every little piece, it takes a lot of time, a lot of effort. Okay, here's the new drill rig right in there. We see our water tanks still here. Here's the drill bit that they're going to use. They're getting set up. We've got, you know, sites ready to go. Here's the next thing that we had to be concerned about, well cuttings. Before, well cuttings were put into ponds with liners, but then well cuttings got a bad name. So what we did basically was that we collected our cuttings into this container here, again covered, and you can kind of see here's the dirt around. It's mostly just dirt. These are rocks that are ground up by the drill that come back up. So one of our future studies was to study these well cuttings and prove that they are not hazardous, that they could be used and probably used in a beneficial way for agriculture. But again, we took them and we kept them in closed containers. Here is the hard part. Basically, we had to get them from this container into this truck here, which is a guzzler, which then would take them, put them into a backhoe here, and then put them into these trucks here, which were then sent to Seneca Meadows out by Rochester, a 3-hour ride away, for something that wasn't really hazardous. And again, this is what I kind of point to. We found that well cuttings were found to be safe to add as fill in landfills. And again, this was a report that was done. And again, they were taking cuttings from Tioga and Bradford County and adding them into these landfill sites in Chemung, Campbell, and Angelica right there. Drilling proceeds at 24/7. It never stops. It goes at night, it goes at day. There's 2 shifts. They both work 12 hours. They're 12 hours on, 12 hours off. Sometimes you're going to hit water deeper in the hole. This is old Connaught water that basically has been there for millions of years. But then you have to bring in what's called a drilling mud mixer. Again, this allows the mud that's then circulated down the hole that pushes the water out of the way and allows the drill to continue drilling. Without it, it would just be bouncing up and down. You wouldn't be doing too much of anything. The next step is you have to make these perf zones, okay? You're gonna get ready to frack. You need to shoot the fracking fluid through some small hole. And again, we have the casing surrounded by cement. And basically, it's an apparatus that comes in. It's mechanical, and it blasts through the casing right there. Small, maybe 1 inch, 1 1/4 inch holes that go through. And again, basically what you're going to try to do is frack through these holes here to set up your fractures. Now, the question is, how do you know that, what a company has done? Publicly, they have to fill out what's called a completion report. Again, you can find these at the DEC website, or the one that I like is asogis.com. That's the one run by the State Museum. And here, they ran 51 shots. This was the Pullis well. And again, it even tells you how many gallons of water that they used, basically the amount of pressure over here, a lot of information. And then it tells you what intervals that they shot those holes in. It's kind of a lot. So if you really want to do your research, you could find this documented all over the place. The last but not least thing to run is the cement bond log. Again, I direct you back to asogis.com if you want to find if they ran other cement bond logs, but basically this log will tell you whether your cement and casing job is whole or if there's any defects. Running a log is just pretty good insurance right now. This is what we waited for the long whole night. Frac ingredients. Okay. What is pumped down into the hole. Basically, it's 90% water, roughly 9% proppant, which is mostly sand on occasion, but we'll talk about another proppant later. And the other amount is frac fluids. That's usually less than 1%, okay? So again, you're diluting a big mix. And these are the type of chemicals that they use. What happens is as you go down deeper into the hole, it gets hotter. So basically, you want to prevent scale deposits, you want to prevent bacteria. What's diluted acid for? I don't know. I've been told that the geology departments don't use HCl anymore, but that's like a no-no. When we were in geology, we used this all the time, and again, we were looking at limestones or dolomites. But again, this is used in the process to dissolve the cement around those little holes that we just made with the perfs. Sometimes you just don't get a clean open cavity, and this helps it dissolve it. And then the other thing is, if you know anything about the mineralogy of both the Marcellus and the Utica, some portions are calcite rich. So again, this helps dissolve the cement between the different minerals that hold the matrix together. And again, it just helps to make better fractures. So here's the fracking operations. This started to happen in November 11th, 2009. We used 79,000 gallons of water. Again, that was the maximum allowed, and these were when the rules were written back in 1982. It was an arbitrary number. Again, they could have made it 1 million gallons at the time, but again, most of the wells that we saw fracked in Medina, fracked in Chautauqua County, they were using anywhere from 20 to 40 to 60,000 gallons of water, mostly on the average of about 20,000. So again, they thought they had the limit, 80,000 gallons. Well, our boss, Orville Cole, he wanted to invite not only the DEC, the SRBC, the health department. We had ProPublica and the Sierra Club on site the day that we were fracking the Ross 1. A lot of stress, but Universal Well Services did the job. You're going to be hearing from Roger in the near future, I think. Is that correct, Mark? Yeah. Again, he'll probably describe this. His crew came out and did a wonderful job. And we'll take a look at some more pictures here of how complicated this process is. And this is where the truly dangerous part of the process is. And let me just further develop something here. You see big pictures of the Pennsylvania sites. What I want to bring your attention to is they're mostly bermed. You'll see a bermed wall around the Pennsylvania sites. They're about 5 acres. And basically what they're geared to do is kind of prevent frac water from getting all over the place in case of a blowout, just like we had in Bradford County. Now, I hear all types of different reports. Until the dust settles, I don't know really what happened down there. But here's the proppant. Here's the sand. They get mixed in an area over here. Here's our water. Again, another sand truck. Again, a boom here to lift heavy equipment, which we'll take a look at. Remember, we used drilling mud. So again, what we did is we put 2 tanks over here that we could reuse that drilling mud in the future, somewhere down the line. Over here is the stormwater prevention pit. Notice how the water keeps traveling off and into it. Here's the flowback tank here. What will happen is eventually all these trucks will leave. The water will be, or at least the well will be flared. The water will separate out here, go into this flowback tank. It'll collect there, then back into those gray tanks. Here we see the pumping engines right here. Again, lots of pipes. Here's the chemicals back here. I don't know, can everyone see those? You can kind of see the white tanks that they sit in. And they come in on one truck, and that truck is parked way back there. Here's a closer look of it. Here's the pumping trucks. You can see basically 1, 2, 3, 4, 5, 6. 6 pumping trucks, 7 over here that you can't see. Again, here are all these lines. These are what have to be secured. This is the part of the process that's dangerous. Again, they're fed into different lines, eventually fed right down into the well borehole. Again, the water being over here. Again, lines coming in. You can see this pipe coming over and down into the well bore. Again, fed at pressure that this pipe can handle. Again, remember we had to set our well casing and we had to tell them our design? Well, without that design and without knowing what type of fluids and volumes that we were going to put in, again, they couldn't tell us if the casing that we were using was correct or not. Again, a lot of planning is put forth. After the frac is done, the water is tested. And again, it's taken from these tanks here. And the test, remember, this was done in mid-November. The test took about 42 days. We had 45 days to get the frac water, which were held in these gray tanks, off the site and disposed of. So testing took us 42 days. So I think somewhere down the line, they've got to change that timeline somewhere, because that was really cutting it close. Again, this is the frac water analysis. Again, you guys will be seeing this, I guess, because we're going to be leaving these slides here. If you want to take a closer look, I'll leave my email or anything like that, and I'll send this off to you. It's 55 pages. So you can really take a closer look at what's going on here. Again, this is what we've tested for. And this is just the executive summary. So what the two most important things to look at in the frac fluid are TDS and chlorides. Basically, these are the things that are going to show up in wells. You're going to see a high TDS count, and you're going to see lots of chlorides. Again, the total dissolved solids from the Ross 1 after testing was 6,460 milligrams per liter. Chlorides were 5,070 milligrams per liter. This represents 3% of what the Watertown public wastewater treatment plant can handle per day. 3%. So not only could they take our whole load and dispose of it in one day, again, they could take back a lot more. And consider this. Now, when they fracked the Marcellus, and we hear 7 million gallons of water and frac fluid, but only 20% comes back out. So again, we're not disposing of that 7 million, we're disposing of 20%. Can wastewater treatment plants handle it? Yes, if they're certified to do so, and again, they're equipped to do so. And how do we know that? With the Headworks analysis. Again, before we were allowed to do anything, again, we spent almost a year getting a permit. One of the conditions that we had to submit is pretesting toxicity. So again, the Flowback was tested on their aerobic cultures and their anaerobic cultures. Again, 35,000 gallons, and that was not the total. We sent 32,925, somewhere in that ballpark. Could be directed directly to the anaerobic digesters or in the Headworks facilities. So either way, we were covered. The bacteria loved it, wasn't, fighting it or doing anything else. Another test that we had to do. After the frac fluid was brought up to Watertown, they spent 35 days testing the fluent that was coming out of it. And again, this was done because the Division of Water, Bureau of Water Permits, wanted this done. Again, this is available not on our website, but basically Otsego County has most of our data. They do a better job of getting it out to the public than we do most of the time. So, here comes the big problem. Well, 45 days, that puts us somewhere in around January 1st, and what do we have? Lots of snow, and all these tanks are pretty much frozen. So what we have to do is bring in these heater trucks that basically heat the water up, pump it back in, heat more water up, pump it back in until they basically become warm again. And what's interesting about that is it was cold that day, so most of the people were huddling the tanks. They were really nice and warm. So this is what the tank looks like after it's cleaned out. You can basically take a look and again see that there's nothing in here, and this is how they have to be returned. So again, we had 6 trucks that went up on these cold days, and this is how many gallons they took, and this is what it broke down to be. Again, the chlorides weren't a lot. You're looking at 5460 as far as the average gallons, chlorides, toluene, total solids, suspended solids. We were wondering where the toluene was coming from. And it wasn't in the frac fluids. And there was a study done by Bruce Selleck and his students out in Colgate. And they were starting to take a look. And then we must have hit some good fractures in the Utica, because if you take a look at what they found toluene in their samples too. So, again, typical daily loading represented 3.1%, suspended solid less than 0.2, 3.8 for total dissolved solids, toluenes 1.3%, 4.8% chlorides. Without this knowledge, you're not sure whether your water treatment plant can handle it. This is why Headworks analysis is important. This is why testing is important. Without it, we can't move forward. What we did not test for in our baseline testing, we did not test for coliform, nitrate, nitrites, surfactants, or hydrogen sulfide. This is coming back to bite me. Hydrogen sulfides. How do I know when there's hydrogen sulfide? Everyone knows about the rotten egg smell. When you walk into a house, if you have hydrogen sulfide, you're going to smell that rotten egg smell. But again, this could be seasonable. It could happen in the winter and spring when the water table is a lot higher, and you won't smell it in the summer and fall. So again, as part of our new testing regime, we're going to start to test for that, because we want to document those seasonal changes. This gets us into water well testing. And basically, I'm going to show you two results here. Basically, what we've done is we've been testing almost quarterly in a certain amount of wells, not all the wells, but a representative sample that goes around the radiuses. And again, they were tested in 2008, 2009, 2010. And if you notice here, the water changes, but not by a lot. Everyone can see that? And even if you take a look up here, it basically remains the same. And that's what we're looking for. Well B, again, tested in 8/6, 2009, 9/30, 2009, 1/13, 2010, 4/20, 2010. This is the standard for drinking water right here. This is the testing. Again, sometimes it goes down. Sometimes it goes up a little bit, but it basically remains and stays within the ranges. That's what makes us confident that we're not contaminating the aquifer or anyone's water well. What we want to look for is spikes in total dissolved solids. Notice over here, 220, 190, 162, 190. We're not seeing that. Chlorides, 2, 2, 2.5, 2.6. If you see elevated levels there, the other good indicators, sulfates. Again, 6.6, 5.7, 11. Still staying within a range and in water drinking standards. Without doing this testing, we don't know that. And now we have data after 1 year. So we have water wells. Well, here's the standard again. Here are residential wells, the range before, the range after the average. Surface water, ponds, range before, range average. 2006, the USGS tested 8 wells. And here's our flowback. So you can take a look. Again, this is available at the Otsego County Planning website. And how we're going to do this is we can't tell you the exact concentrations in a well with a name on it or a property owner's name. But what we can do is tell you the ranges. And this becomes pretty interesting because we can take a look at these ranges before and after and see that they don't change too much. Again, before and after. Before we drilled, these were the ranges that were used, and these were the ranges that we found in our flowback. So it's pretty easy to compare and see, are we telling the truth or are we not telling the truth? And now I want to point out one thing over here. USGS tested 8 wells. To date, we have tested close to 152. And at times, and you saw from well data A, B, and there's more, we tested them multiple times. And again, it all relates back to geology. Where we see the high strontium and barium, see this pink area? This is the Marcellus outcrops. When people have water wells that go through this type of bedrock, they have that certain type of signature. It happens over and over again. Now, I talked about, finding methane. And what we like to do now is we like to type things. Here's our Utica gases right here. Here's a Herkimer gas analysis from Madison County. Now, here are two shallow water wells roughly about 25 miles away, again, that were tested for methane back in 2007. Now, here's an area, these red dots, where we were interested in, and basically we found methane in the water. We tested them. Mostly this is microbial gas, not thermogenic. Some are in wet thermogenic gas, but this methane comes either from this methane here or it's a lot different. So you can make up your decision one way or another. But again, testing for this type of data, this is the new thing that we're starting to do. It's kind of fun. It's not so bad. The well cuttings study. Remember, we were getting rid of all those well cuttings to Rochester. Those could be used for soil buffering agents. So we basically contracted a study by Bruce Selleck and his students at Colgate University. We took a look at the mineralogy and the geochemistry of the well cuttings. We found nothing bad. We want to do more testing, but we didn't find anything that we could say things would be bad. We're developing partnerships. We want to work with local groups. What we've done is basically work with the U.S. Water Resources Division in Troy and Ithaca, State Health Department, SUNY College at Oneonta, Otsego County Planning Office, Soil and Water Conservation District, and an invited industry partners. We want to put together a database that we could bring out to the public and say, you don't have to worry about your water, because we're worrying about that for you. And what's interesting is when you develop partnerships with the USGS, one of the things that we want to do is we're going to be drilling new wells pretty soon. And before we set the surface casing, we're going to have the USGS bring in their tools so that they could determine where the water aquifers are and their depths before we even set casing. You put this database together, you've got something powerful. And if we do it from town to county all over this state, you've got something really, really special. Again, we've sent out our frac fluid to West Virginia Water Research Institute, USGS in Reston, Virginia, and Ithaca, New York. The New York State Health Department is testing currently a Marcellus flowback that we had that we'll talk about. And Dr. Stephen Osborne of Duke University basically did some independent testing. We will look to send samples and get more data from anywhere we can get it. We don't want to pay for this data, but again, these are willing partners. Again, objective observers. Now, this brings me back to this point again, this chart. I'm starting to fall in love with this chart. This is bad. Again, this is independent testing from Dr. Steve Osborne of Duke University. He was recommended by Trout Unlimited, and we invited him up at no cost to ourselves on his own dime, but we wanted him to test our residential wells, 13 of them, and basically see what his results are. And basically, here are our results here are his results. The numbers fall almost exactly in line with each other. They do not change. Again, independent testing. We tried to get the health department to do it, the DEC, no one would do it. It's like a broken record. But again, if it's done, we can see it. We then applied for the EPA study and basically got selected as a candidate for possible baseline water quality data. You can see we're doing the type of testing and developing the type of relationships that we need to. And again, I think this is where the industry is going. There's the Ross well in the summer of 2010. You have to reclaim the land. Does it look much different? There's the well right there. Grass is growing along the hills, access road. We weren't too happy with this, so we decided to frack the Marcellus. So here, this is one of the things that This time, we weren't using 80,000 gallons of water. We were using nitrogen. We used about 7 million cubic feet of nitrogen and about 18,000 gallons of water. So again, what we were doing here is we're fracking the Marcellus. And one of the changes that we made, we had such a mud bowl on occasion that we brought in these reusable 3-ply mats. They're made out of hemlock, and they're basically about 10 foot square, and they just rest right next to each other. And it was like a pleasure, you know, just walking on this as opposed to what we were walking on with the Utica. Now here is this special proppant. This is a composite of carbon, and they're very round sphericals. So round that, again, you could get great porosity through this once they're put in the hole. And why do you want to do that? Because basically, as you can see here from a Marcellus core in Chenango County, the upper part of the Marcellus, and again, it's more silty or quartz rich, and as we get toward the basal part, it's definitely more calcite rich. Again, just knowing what you're doing helps. Here's a close-up of these spherules. Now everyone says, let's put some type of trace in these rocks. If we all use this proppant, these things, they're still coming up in my truck. I can find small little sphericals all over the place. I don't know how they make it there, but they're all over. And again, they're light, they're easy, and again, the nitrogen foam type frac help push these proppants into the fractures. Again, what happens is basically all those trucks leave, and it's hard to tell. Let's see, in this picture, right here, the well is kind of flared, okay? And the water comes through here, it goes through a glycol separator, then comes out into a flowback tank, which again is pumped into those gray tanks. Now, using this flowback here, we had a problem. That lightweight proppant, it was hard to get rid of. We didn't really know what to do. So what we did is we brought in these dewatering tanks, and what we used, what we used was sawdust, and then we started to put the water in. And again, the proppant would be trapped in the sawdust, and the water would come out, and it would be pumped to that tank right there. Now, in this time, when we did the flowback for the Marcellus, we didn't dispose of the flowback at Watertown. We took this flowback to an injection well in Ohio. So, lessons learned. Will the Utica flowback chemistry change when a larger amount of water is used? Yes, I already know the answer to this, and the reason that I know the answer to this is in Canada, where gas stem is located, and we've drilled a few wells. We're looking at the flowback from those bigger fracs there, and the change is not much different. I'd like to present it tonight, but I wasn't allowed. Do we need more study and documentation to show that hydrofracking does not affect groundwater? I think we do. I went to a recent conference, and basically it was put on by the USGS, and the flowback changed colors from day 1 through day 90. Do we know all the answers yet? I don't think so. But are we getting there? I think we are. Will new supplemental guidelines be in effect by the end of this year? Maybe, maybe not. Again, the DEC is talking about the summer. What does the summer mean? The way I'm reading the tea leaves these days, it'll probably be sometime in August. So basically, I don't think we'll see permits, if they do happen, until the beginning of the year, or maybe second quarter next year. Again, I'd like to thank Mike Sligar, who was the chief operator in Watertown, Aaron Sulke, who's our environmental scientist, who's doing all this water work, Tiffany McGivern, who did the initial work, and her advisor, Adam Schoonmaker of Utica College. Thank you, and I'd be willing to take any questions you have.